So this setup works for scattering objects upright, but what if we wanted this to follow the normals of the landscape? To make this easier to demonstrate, let's just duplicate this sphere node. I'll hide the other geometry here and zero out these transforms, jump inside, and give this sphere some point normals, as at the moment it doesn't have any. So let me just drop down a facet node and set this to post compute normals. Now we get some normals on the points. We can see them here by activating this. If I want to make these bigger, I can go to the display options by pressing D in the viewport and increasing the size of the guides here. I'll also delete half of this sphere just by putting down a delete node. Set this to bounding box and change the scale and the center. Now if I drop down a scatter node, you'll see that the points or the normals of these points are transferred onto our scatter, which is awesome. And to make this a little easier to view, I'll just use a copy swap and copy a cube onto these points. So let me use copy stamp. The points go on this side and drop down a cube. Increase the size, and we need to make sure its base is set to the origin. We can do this pretty quickly by channel referencing the value on the y-axis. If I copy and paste that here, and halving the value, this will keep the base on the origin. And I also want this aligned to Z, as that's how the copy swap works. So let me just rotate this by 90 here. Now it's pointing in the Z-axis, and if I plug this in, you'll see we have it all working. Let me just turn off these normals for now. Cool. So what if we want to randomize the rotation here like we did previously? Now, we could do this in an attribute wrangle, but instead let's do this in VOPs just to make it a little easier for us to understand. I'll drop down an attribute VOP, jump inside. Now the easiest way to do this is to write into the up attribute, which exists already for these points. So if we drop down a bind, set this to up. Up is a vector, so we need to choose vector from the drop down, and set the export to always. Now if we want to rotate around this axis, we can drop a rotate node down and set the axis to the normal axis and plug this in to the up. Now you'll see this doesn't work because we are trying to plug a matrix into a vector. To get around this, we can just multiply the axis that we want to use on top of this rotate. So if I drop down a constant, set this to vector, and we're using this axis here, the y-axis, I will multiply this on top. And now we get a vector output. Cool, so if we use the angle rotation now, you can see we can rotate these around the axis. But what if we want this to be random? So let's just randomize this value by using the point number input like we did before. So let me just plug this in instead of the angle. So now I will get a new angle for each individual point, but this isn't really controllable and doesn't make much sense in terms of angle because the point numbers go from 1 to whatever the number of the highest point is. To fix this, let's just randomize these point numbers, which gives us a value back between 0 and 1, similar to what we did with the fit01 in the attribute wrangle previously. So drop down a randomize. Okay, now we get a random angle between 0 and 1, and this is easier to control. Now, what if we wanted to control the amount of randomization? We can do this using a fit range. So if we plug the output here into the value and plug this into the angle, we can reduce the destination max, which reduces the amount of randomization. To increase the range though, let's set this to -1, like we did on the wrangle previously. So this is great, we get the full range. Now if we wanted to rotate on top of this randomization, we can just add a constant value to increase the angle overall. So let me just go here and put down an add this in here, and drop down a constant. Now if I change this value, we increase the overall rotation on the axis. Cool. Be sure to add this constant on top. If we want to be a little more accurate than this, then the rotate node actually works in radians, so we can drop down a degrees to radians here. Cool. So if I remove the randomization for now and switch this to integer, now if we rotate say by 45 degrees, it's doing what we expect. So it's actually rotating around a predictable amount of degrees. Now the last thing I would want to do is make this more user friendly by exposing some of these parameters to the top level. So to do this with the randomization, I would just middle click, promote parameter, and double click to bring this out. Now we also want to change this from 0 to 180. Let me just add this in to 180. And for the min, we just want to take the negative of whatever value we dial in here to make sure that as we lower it, it's getting lowered on both of these values. So let me just use a negate to get the negative value and plug this in to the destination min. If I do this at top level, so we get the full range, you can see its effect. I'll just rename this to randomization on the Y and change its parameter name to rand Y. Now I need to do the same with the rotation here, so let me just promote this, change this to rotation Y or rot Y since this is the attribute name, and then the attribute label to rotation Y. Again, I'll change this to 360. Now on the top level, we have the option to rotate this and also add in a little or a lot of randomization. Cool. And it all follows the direction of the input geometry. Now the next thing we might want to do here is to add some clumping to these points. So to do this, I'll drop down a fuse node. Let me just make some more space here. Now fuse just brings the points together. Let me set the snap distance to something like 1.7. And what the fuse node does is it also removes the points that it fuses together. So we want to untick fuse snapped points, and this keeps the number of points the same. You can see we have 1000 now, whereas if I leave this switched on, we only have 280, but we want to keep this for now. So to get a very simple clump, all we need to do is drop down a blend shape and blend between the fused and the unfused points. You can see we get a nice clumping here. It's very uniform, but we can deal with that later. Another thing we can do, and to make this more obvious, let me just increase the amount of points here, is we can control the p-scale value based on its proximity to these clumping points. So the easiest way to do this is to copy and paste the fuse and channel reference the snap distance to make sure this is consistent between the two fuse nodes here. You'll see this is now referencing the fuse 1 to L3D, which is here. We will create a p-scale attribute for both of these, setting 1 to 0 and 1 to 1. So like before, we will use the attribute create. We want the snap points to be 1. Change this to p-scale. Copy and paste this. And the scatter points to be 0. Make sure this is 1. And finally, use the attribute transfer like we did previously. So let me go attribute transfer. To and from. Switch this to points and pick p-scale. And now if we look through the copy SOP and increase some of these values, you can see that we get this fall off from the center to the edges. Let me just change the fuse amount here to make this more obvious and reduce the blend shape. And then blend this a little further away. Cool, so now you can see the clumps actually go inwards here. Nice, so it's a little uniform still. If we want to fix this, we can add a point jitter, which will randomize the position of the points. Make sure not to update the normals. And we can affect the scale. Cool. Just playing about with some of these settings here. Now, two things to bear in mind with the point jitter is one, we can use this to just jitter the p-scale as opposed to the point normals, which is pretty cool. And also that it will begin to lift the points off the surface that you are scattering on. So to correct this, we'll just use array node, which will bring the points back to the surface. So the first input is the points, and the second is the input geometry, which we created up here. Let me just zoom in and make sure this is set to points. Cool. Now what this is doing is it's actually taking the points inside the sphere and sticking them back to the sphere itself. So if I turn this off, you can see that. Now we want this to happen, but we also want it to happen for the outside of the sphere. So I'll just copy and paste this again. And this time on the second one, reverse the rays. And that sticks the ones on the outside to the sphere too. Cool, so now we have everything stuck to the sphere again. And we have everything working. Finally, just for efficiency, after the point jitter, let me just fuse these points together again to get rid of anything that is getting too close. I can lift this quite high before it starts to take any effect. So this is probably fine. And again, don't affect any normals. Sweet. Now, if you want to control the min and the max p scale a little bit better, you can do that in the attribute create, or alternatively, you could build this into a VOP and randomize the p scale to blend it with the clump fall off. This is similar to what we did when we wanted to randomize the rotation by using the point number in the attribute VOP, but instead of me demonstrating this here, I believe that you have enough information that you could work this out by yourself. So this will be part of the assignment this week. Now, we've covered a lot of useful tools in this lesson. And the last thing I want to mention quickly is the paint node, which allows you to paint any attribute. So for instance, you could go ahead and paint the P scale. So let me just disable all of these nodes for now, right up to the scatter node. And move them out the way. I'll just plug the scatter back into the copy swap here. Oh, a bit too far away. And if I go to the delete node, let me just switch on the wireframe. I will probably need some more points, as when we paint onto the geometry, we're painting onto the point. So let me just subdivide this a little and drop down a paint. Attribute paint. I also want to create the P scale again, so I'll just take this, make sure it's set to 0, and plug this in here before the paint. Okay, so the paint node will automatically try and paint a mask for you, but instead, let's make sure we switch this to P scale. Now this will disappear, but we can bring it back by adding a visualizer like we did before. And now if we hit enter, we can begin to paint the P scale attribute. And if we use that in the copy swap, you can see it works just fine. Obviously, this is going from 1 to 0, but we can be a bit more nuanced if, for instance, we take down the opacity and then begin to paint this in a bit. a little bit more. Nice. And like we mentioned before, with the scatter tool, when the density followed the sphere, we could also make a fall off between the geometry and the p-scale value. So anything closer to the sphere is bigger and anything further away starts to decrease in size. So this is all I wanted to do for this video, and I really hope that you're beginning to see the power of everything that you can do in Houdini for scene assembly. Houdini's tools, mixed with its easy coding system and simulation tools, make the learning curve more than worthwhile. And although Mash and Forest Pack, for instance, are incredible tools, for easy customization without going into pure coding, Houdini wins every time for me. So next up, we'll take a quick look at the Game Engine Physics tool. Thanks.